Hello. In the previous video, we learned how to interpret the mean as a mean of a binary distribution as the probability of success. So the mean of a binary distribution doesn't mean anything. So we have to interpret that as a probability, but we can utilize exploit the nice properties of the mean. And in this video, I'm going to consider another example. Think about a multiple choice question. You can think about your online homework. In your online homework, I believe, you have you have finished homework 1 at this point, at this time. So this video is supposed to be uploaded on September 23rd, and the first homework is due September 26th. Still, you must have finished your first homework when this video is uploaded. That's that's how it's supposed to be done, and what I recommend you to do. Anyhow, so the structure in the homework is that you see 5 options and consider a randomization of the answer. You simply randomize what your answer. So you choose one out of 5. Of course, you may be correct, you may be wrong with chance, and we know their probability. So if you randomly choose one of the 5 choices, then the probability of correct. So I am going to so this randomization results in either you are correct or wrong, and I'm going to call the correct answer as success and denote it as 1, and wrong answer as failure, denoted as 0. In this case, success is better than failure, but you may change success and failure if you want. Anyhow, so probability in this case, the probability of a correct answer is 1 out of 5. Out of 5 choices, only 1 is correct. So if you randomly choose 1, the probability of being correct is 1 out of 5, which is very intuitive. So we can write this experiment as the outcome X follows a binary distribution with probability 0.2. This is how we denote the distribution, binary distribution. It loses no information about what I said here. And now I want you to find the expected value of X. And because we already know the full probability distribution table, you can calculate the expected value. So try this, do this, and resume the video when you finish calculating the mean. Let me turn 3, 2, 1. The answer is 0.2. So first, you may simply choose 0.2 because I said using the property of the binary distribution is that the property that the mean equals the probability of success. The mean and the probability of success are always the same in any binary distribution. So in this case, they are the same. They should be the same. So 0.2. So we know the probability of success as 0.2. So the mean then automatically follows. So without any algebra, you should be able to get the mean if you understand, if you know the property. But if you can't believe the property yet, I also understand that, and then it's not bad to check if it's really true. So outcome probability, and if you multiply, we get 0.2. 0.8 multiplication gives 0. So probability weighted outcomes are 0.2 and 0. If you add them, the mean is 0.2. So this is the mean, which is the same result if you used the simple way. Okay, if you change the number, So change the parameter from 0.2 to any number you want. Of course, it has to be a probability, like greater than 0, smaller than 1. It should be always true. So you can check it by yourself. And next, find the variance. Also, try to find the variance, which is our next step. Pause the video and resume the video when you're done. I will turn the page in 3, 2, 1. Here. So remember the variance. And the first step in the variance is to calculate the mean, which we did in the previous question. So the mean was 0.2. So square deviation, I transformed x into square deviation in one step. Subtract the mean, and then 1 minus 0.2 is the deviation. And square it, so then it becomes squared deviation. So you get this, and do the same thing for the other variable, the other outcome. Then you get square deviation. And next, these square deviations should be weighted by the probability. So weighted squared deviations are these. So the variance is 0.16. 0.16 is the variance. And then 0.16, we are going to study what is this number? This number, where does it come from? That's simple. You may think it's multiplication of these two guys. Yes, that is right. That happened to be the correct answer. So let's think about the general algebra using unknown p. So we are going to derive the mean and the variance in the very general setup without specifying the value of p, but leaving it as an unknown variable. So p and 1 minus p are probabilities. And outcome times probability is p. Outcome times 1 minus p is 0. So 1 times p, 0 times 1 minus p. So anyhow, what matters in the end for the mean is p, right? So p equals the mean, and p was the probability of success. So we confirmed our earlier observation. So the mean and the probability of success are the same. Now let's go to the variance. It's a little bit more tedious algebra, but not bad, not that much bad. So square deviations are, remember p was the mean, so 1 minus outcome minus the mean is the deviation, and square it. So 1 minus p squared is the square deviation for the first outcome. And outcome 0 minus mean and squared. That is the square deviation for this outcome. And then these square deviations has to be weighted by the probability. And 1 minus p squared is multiplied by its probability p, and 0 minus p squared is weighted by its probability 1 minus p. So it's complicated, but what you need is the sum of them, the summation of them, which equals the variance. So variance is sum of these two guys. First, expand. And expansion is not that bad, and it cancels out a lot of things. Cancel out. Then you have minus p squared plus p, which can be written as, factored out as p times 1 minus p, right? So then you just derived the formula that the variance of a binary distribution equals probability of success times probability of failure, right? Success and failure, right? In this case, we can simply obtain the variance by multiplying two probabilities. One thing I'd like to say, here. So the variance of this is a powerful result. So probability of success times probability of failure it makes the variance of a binary distribution. In our previous example, we obtained 0.16, and which equals the probability of success, probability of correct answer, times probability of wrong answer. And again, one important point here you have to observe is that still we need only one parameter. So if you know P, you know this, so you know everything. The variance can be calculated from one parameter. That's all you need to know. So the parameter is a perfect information about this distribution. And another thing that I did not mention here, but should have been mentioned, was that when you calculate the mean, in this case, if you change 0 and 1, so if we use 1 for correct answer and 0 for wrong answer. But if you change the encoding, say 0 for wrong answer, in like 1 for wrong answer and 0 for correct answer, then the mean will be changed because success. So if 1 stands for correct answer, the probability was 0.2. But if 1 stands for wrong answer, then the probability will be 0.8. So the mean would be 0.8. So the mean depends on what is denoted as 1, right? So if you change 0 and 1 in the definition, then the mean would change. However, even if you flip 0 and 1, does not matter. In the end, you are going to multiply two probabilities. It doesn't matter what you multiply first and later. Does not matter at all. So variance does not depend on what you define as success and what you define as failure. Variance, it does not change. That's another property we can find in here. And I'll give you an intuition why you have to multiply them. So I will think about different values of the parameter. 0, so 0, 0.1, 0.2, 0.5, 0.8, 0.9, 1. So there are the two extreme cases. 0, in 0, there is 0% success. So always failure, and 1 is always success. In these two cases, so for each parameter value, you can calculate the variance, and both extreme cases have 0 variance. It's very interesting. The reason is that, remember, the variance is about dispersion, variability. But in this case, if always failure, there is no variation, no variability, always 0. And if it is always success, there is no variability. It's perfectly success. So in these two extreme cases, the variance will be 0. All the outcomes must be the same. And even if it's not 0, if it's close to 0, similar idea will happen. Similar thing happens. So suppose that there are 10% probability of success. In this case, 90% of observations are failure. Most of the observations are failure, and a small number of observations have some kind of deviations. So they vary only on 10% of observations. So as the probability goes to extreme, toward 0 or toward 1, like you can think it this way. Variance captures uncertainty in your distribution. But if the probability is going to 0 and 1, the outcome is kind of predictable, right? Outcome is kind of predictable. So then there will be little uncertainty. So for example, suppose that you buy Powerball lottery, Powerball lottery, then I can expect your result. I can expect what the outcome would be with a very high probability. I will predict the result to be $0, right? So it will be nothing. Then my prediction will be correct with 99%, I think. So like that, if it's 0 and 1, close to 0 and 1, there is little uncertainty and the variance will be small. And on the other hand, the variance is maximized at 0.5. This is the point where the failure and the success are equally likely, so the most difficult case to predict. You cannot predict at all. So whatever you choose, you lose the same probability, right? So 50-50. So it's the the fully uncertain case, so the variance is maximized. This is why the variance takes that shape. That's I try to explain it as an intuitive way. Okay, in the next video, I will extend this model to a more complicated case. The main topic, binomial distribution, will be introduced. Okay, see you later.